There are lots of other systems that have a similar feel to what we saw in the pendulum. They are oscillators. Here's an example that is similar to the pendulum that we just looked at, but it's maybe a little bit less familiar. This is going to be a spinning pendulum. So we're going to take the same setup that we had before. We've got a pendulum, and it goes back and forth at some angle theta. It's got no friction, so it's just doing its thing. But now what we're going to do is put this planar pendulum into a box, and we're going to spin that box about the vertical axis at some angular speed. We're going to call that omega, and this is going to be a constant. Now, in this case, one can do a little bit of physics, write down a model for how that angle, theta of t, evolves over time. And the second-order nonlinear differential equation that you get in this case, getting rid of the mass terms, is L times the second derivative of theta with respect to t is equal to L times omega squared times sine theta times cosine theta minus g sine theta. Again, just like before, L is the length of the pendulum, and g is the gravitational constant, and that omega is that angular velocity. Now, what we're going to do is convert this to a first-order system, introducing a variable v that is the derivative of theta with respect to t. In this case, the first-order system on theta and v is given by what? Well, the derivative of theta with respect to t is by definition v. The derivative of v with respect to t is the second derivative of theta. Taking that formula, dividing out by L, we get omega squared sine theta cosine theta minus g over L sine theta. Next, we're going to take this system, solve for the equilibria. Clearly, we need to satisfy both v equals 0 and factoring out a sine theta, we get sine theta times quantity omega squared cosine theta minus g over L equals 0. Now, because of that factoring, there's an or situated in there. Working with sine of theta first, we see that we have a couple of familiar solutions. The first being at 0, 0 at the origin. The second being at plus or minus pi, comma 0. Again, because we're on the circle, that is just a single point corresponding to the pendulum at the very, very top. Now, where it gets interesting is where we look at that second factor, where omega squared cosine theta has to equal g over L. That means that cosine of theta has to equal g over L omega squared. Now, we're going to assume that omega is sufficiently large, that you're really spinning the system around. If we have omega bigger than square root of g over L, then we can solve that equation for theta, and we get a new equilibrium at arc cosine of g over L omega squared, and v equals 0, of course. Now, here's where you got to be really careful, because arc cosine is really going to take on two values, one positive and one negative. This is going to lead us to a case where we have 4 equilibria in this system. Our next step is to compute the derivative. Looking at the right-hand side, f of theta and v, we can compute the derivative as follows. The partials with respect to theta are, first of all, 0, and then, the hard one, omega squared times quantity, cosine squared theta minus sine squared theta, minus g over L cosine theta. That's all the partial of the second term with respect to theta. The partials with respect to v are simply 1, 0. Okay, now in this 2x2 matrix, the trace is always 0. The determinant is either going to be positive or negative, hopefully not 0. That means that we're going to have either centers or saddles. Now, what about those centers? Well, the fact is that because this pendulum is frictionless, once again, we have a conservative system so that we're really going to have true centers wherever the determinant is positive. So let's use this to classify these 4 equilibria and see how it compares to the ordinary nonlinear pendulum. First of all, at the origin, what do we have? We know the trace is 0. The determinant, when you evaluate theta and v at 0, you get g over L minus omega squared. And this is going to be negative. Remember, we assumed that this angular speed, this omega, is sufficiently large. That means that we've got a saddle point at the origin. And this is really a little bit interesting, a little bit different. What happens at plus or minus pi comma 0? Well, now the determinant is going to be minus g over L minus omega squared. That is definitely negative. That means that we also have a saddle here. So it looks like we've got saddles everywhere. What about this last pair of equilibria? At plus or minus our cosine of g over L omega squared comma 0, the determinant is... oh, it's messy. I'm going to let you bother with that. I'm going to tell you, and you can trust me, that this determinant is positive. That means that we have a pair of centers, and this is where it gets very interesting. At this point, we should think about what we have found. Take a look at this system. It's really unusual that you've got this saddle point at the origin. There's no longer this stability where you've got this center at the bottom. If you're rotating this system around fast enough, you are pushed away from that equilibrium at the origin. It's really an unstable saddle. And these two equilibria off to the side have now inherited that stability. And although you're not converging to it, although you vibrate around it like you do with a center, still you have this sort of stability associated with these 2 points off to the side. That kind of makes physical sense if you're spinning this thing around hard enough. This is a really interesting system to think about.